I have got no idea what's been recorded. Doesn't matter. Right, so name of the module, materials part 2. You probably can't see. Move this out of the way. And right, the learning outcomes, all this will be online for you. I'm not going to read word for word, it's a bit boring. However, this is what I want to talk about. So this is our program for the term. You're going to have to do some exercises, courseworks. So you've got, if I go forward one page first of all, I'll explain. Hi Taylor. We've got formative assessments and we've got summative assessments. Your summative assessments are lined up like this. This is where the choice comes in. It used to be when I first took this module on, I would do this as one coursework, right? And people would genuinely fail it. I don't know why they could, but they actually would fail it. The reason being, they would put it off and put it off and put it off. We'd do all the lab test work, but they put it off to the last minute, then submit it. Then you've got 2 other modules that you're also doing, and then it would be just too much. So a couple of years back, well, more than that now, I've separated this up into 3 bite-sized chunks. And what we decided was, if you do the first one, all 3 are pretty much exactly the same. I'll give you an example of the 3. As long as you hide your phones and don't record. I'll show you how some of you got 100% on all 3 of them. I'll show you how they look. Right. But if you do the first one, I'll give you written feedback on how to improve it before you submit the second one. Then you submit the second one, I give you more written feedback before you submit the third one. So you got a chance to improve that mark as you go. Word of warning, this is only worth 30%. Okay? All in. That whole thing there. It's not worth losing sleep, going bald like me, or going grey like me. Just keep it in context. Keep it quite short. I'll give you it, and I won't give you, I'll only show you in the classroom. I'll do it today. And then I won't show you again, I'm afraid. I'll show you how it will look. I've got permission from this one student to show. That's fine. However, the other way you could do it if you want is do it all at the very end as one report. I would suggest we do it how we've done it the last 4 or 5 years. What do you want to do? Because I always get complaints going, we never get feedback. Well, they do, right? We never, that's not a complaint. They don't actually say that. But, or it's too much work. I'm telling you up front, each of them are only worth 10%. Don't. And also, once you've got the first one, the report looking right, it's copy, paste, change the numbers, do a different type of graph, and a different conclusion, job done. It's copy, paste, fill it out. After you've done the first one, that should be one night and one night only. So it should, and even half a night, to be honest. That's what it should be. I'm making it sound simple, but that's only if you do this other work that I'm going to talk to you about. So, if you like the sound of that, does anybody oppose they'd rather do it as one report at the very end than risk failing? We're all happy with splitting it up, making it simple, right? What we'll try and do is we'll have these submitted quite early on. Like week 8, week 10, and week 11. And that means you've got the rest of it free to go on with the class tests and exams and your larger courseworks. So I'm trying to make this a bit smaller, bite size for you. Right. You've all used Microsoft Excel before. If you haven't, please get up to speed. But what I'll guarantee is none of you will have done Microsoft Excel. Let's check one thing. It's all very well me talking, but I don't know if this is actually recorded. It is recording. Good. That's fine. Yeah. I'm going to be showing you how to do the tasks you need to do. And it's not normal Microsoft Excel. You've not learned it in high school. These are additional things that are quite interesting. You'll need to attend these classes here. It's on the Monday, just to learn how to do what you'll need to do. I make it sound complex, but it's not if you attend and do the coursework or do the exercises. Right. What we have is we're going to be in room A25. That's the heavy structures lab. I think you were there before with the concrete test. Right. Well, we'll be in the larger part of the room and we'll be using one of the universal test rigs. And this one here will be compression orthogonal to grain. Then, oh, okay. No, there we are. I've been stupid. Right. Sorry, I've been still. Right. So here we'll be in the lab. I've been silly. Right. Now there's a mistake here, but that's fine. So on this week here, I'll teach you the information you'll need to know before you go to the lab the subsequent week. On this day here, at that time, we'll be doing the test for parallel to grain. And then here in the morning, we'll teach about the test that will happen on the same day. And then the same thing, we'll teach about the test that will happen on the same day. Right. Steel and concrete, we pretend that the material behaves the same in all directions. Is that right? If we pull it this way or pull it that way, it all behaves the same. Yeah, that's how we assume. Yeah. At the normal engineering level, that's true. At a physics level, it's not quite the same. Concrete, very similar. You crush it either this way or that way. It doesn't overly matter for us, but for like a PhD student looking at the build mix-up, it might be quite different. However, timber's definitely not like that. This is what some people refer to as a very good model type, a very good model of what timber actually is. It's eventually a bunch of cells or channels, or in our case, straws. If I compress my straws down like this, quite strong. If I compress my straws like this, they're quite weak. Does that make sense? If I were to put this texture, press it down, what type of failure do you think will happen? You've all done it as a child. We've all been to McDonald's, grabbed a few extra straws and pressed down on them, haven't you? Maybe I did then. Right, it'll buckle. Yeah, it'll have some sort of shear failure there, won't it? What do you think will happen? Now, we will discuss more about this, not for a few weeks, but we will discuss more about this sort of thing later on. I've got a plastic bag holding these straws together, but in timber, there's a thing called lightning. Lightning is like the glue that holds all the straws and cells together, yeah? If I compress wood this way, what sort of failure do you think will happen? But the last time, it was a shear failure here, wasn't it? What do you say? This way here, what do you think will happen? Don't know yet. Right, that's fine, I'll find that out. Right. So are we happy with breaking up into several bite-sized chunks? And you're happy with if you submit on time, I will give you feedback in time such that you've got a number of days before you have to submit the next one. All good with that? Right, excellent. So we'll just crack on. I will upload this to the middle page because at the moment the middle page has got last year's one on it. we'll talk about the middle page just now. Take it with as fine. So we've got the teaching timetable there, or the elastic diet. We've got some additional recommended reading. That's if you want to do a more deep dive, or you want to get more involved in this sort of thing later on. Absolutely, there's a good reading list there. So this book here is recommended. Sorry about that. So this book here, for those who are okay and comfortable with maths, I would still say it's still a very good book. I would say that from first year all the way up to a PhD, the maths that you're likely to use will all be in here, and it's by example. I've given you the book digitally on middle page. However, what I've also done, I've given you a cheat sheet. Everything you'll need for this module I've put onto one page for you from this book. And this is purely about mathematical manipulation. How do you manipulate an equation to get what you want? I'll show you that in just a second. There's a obligatory module guide. You read that through at your own leisure. I'll not go through it in here. There's this cheat sheet I was telling you about. It's just ways to manipulate or how to convert things. It's all about just changing a formula to get out of what you want out of it. You won't need much more. I don't think you need any more than that, to be honest. However, there are worked examples in this book, which I have given you. Let's have a look at that just now. Yeah. I would say what I'd recommend you do is you download this book and save it somewhere, keep it. It's actually a handy thing to have. I will, however, put this book online as well, as long as you don't grass me up. I'm not too sure I'm allowed to do that, to be honest. But I'll load it up and I'll take it off before the end of term at some point. Okay?
Yeah, just make it.
Of course. These sorts of equations, though, for beam analysis, you'll need to remember the main ones. Okay? The main ones you'll want to remember off by heart will be simply supported with the UDL and simply supported with a point load in the middle. The ones after that, if you can remember the Macaulay method that you got taught last term, then you'll be fine. Right. Two other documents I've put in here. BSEN 408 and BSEN 338. We're going to cover them later on. We won't touch on those today. Right. So what we'll do is we'll just go straight into today's class. Right, go and do yourselves a wee favour, look pad out and pencils, because at the end of this, we're going to be doing some exercises, some tutorial stuff. So I might not have space on the screen to give you all the equations. So if you write some equations down as we go, there's not many of them, I promise. I'll load them up now. Hopefully, when the tenor comes back, we'll actually start. So we've got some exercises we'll be doing. Okay, so we'll do them on the board as we go. Well, not as we got to the end, we'll do them. Right, on that note, well, I'm just buying for some time now for Terra to come back. I think that's her name. This is my equivalent. This is my equivalent of the notes from today's lecture. Right, now you'll make your own version of this. So I went through this material and I've made my own notes from it, and that's what I would call my cheat sheet. Probably won't give you this in the class test. You'll have to memorise some of it. So I'm going to show you my tricks. So I do things that help me. I'm heavily dyslexic. I find it difficult to remember things like this. So I do things that help me. Might not help you, but it might.
Are we writing this down now?
No, you're not. No, that'd be too boring. You want to write stuff down to you actually know what you're talking about. Right, I think we might just have to start, I'm afraid. Ever heard of Hooke's law before? Who's done engineering at Visco? Yeah, what Visco, yeah. We're now doing some work with Lumberton High School, Badgate, and a few others. And some of them have engineering classes, and they'll definitely talk about Hooke's law in there. Right. Rather than me reading word for word, I'll actually just describe it in graph when it comes time to show it in graph. We'll just crack on. Right. We'll just crack on. Right, so this is the learning outcomes from today. Actually, I don't know if we'll have viscosity talked about. Not it, we will. We will talk about viscosity later on, because that's possibly an interesting one. Even though it is covered in one of the other modules. Right, so that's a bit more of a recap from what Juan taught you last year, yeah? You've seen this before. So if I've got a rod and hang a weight off of it, it should elongate. I'm going to call that elongation delta. And so there's your first equation here. Force equals K divided by L times delta, where delta is the elongation or the shortening of the bar. It could be a compression force or a tensile force. So you can write this down, and then KL is the axial stiffness of the bar, how stiff that bar is. This is actually very important. Actually really quite important. I actually want to write a paper on this stiffness thing for a much more complex scenario at the moment. Right. So if I'm going to apply a force onto that, and I've got my elongation along the bottom and my force along the top, I'm going to get a graph somewhat like that. Okay? Like a real live, like a real, what would we call it? To be fair, that's a bit more of an exaggeration, but it wouldn't be perfectly straight lines anywhere. However, we're going to make some assumptions. Now, I can show you real data another time, perhaps, where, in actual fact, this is a bit of an exaggeration. There would be areas that would be more straight. However, Hooke's law makes some assumptions, and they are just that. They're assumptions. If I apply a load, so F0, up to here, and I then take the load off, I would expect my material to go back to its original shape. Okay? Well, first of all, if I find that. However, on this graph, F1 and delta 1, it's going, looking at the shape of that graph, you'll not have covered this yet, but looking at the shape of that graph, I would consider that very unlikely, if I take the load off, that would go back to its original shape. I would find that quite unlikely. Why would that be? Well, let's have a look at this first of all. Force for delta, K is stiffness divided by L, whatever, right? From equation 1, we've got these here. You've got two lines. Let's have a look at what KL is then. I can shadow on that, yeah, I can. Right. For just now, assume that the load will go back to its original shape for just now. But look at the angle of the line. If the angle of that line is quite steep, what does that tell you about the material? Think about the elongation along the bottom versus the force along the top. Would you say that the stiffer the material, or the stiffer the load, less deformation, that you've got actually a steeper angle? Would you agree to that?
Yeah.
So the first part, if you only put a small load on it, right, then it's going to act fairly stiff. If I put a much bigger load on it, right, because of the shape of that curve, we can see that the angle is much less. Well, we're going to refer to that as stiffness, right? But remember, this one's got a lower load and this is a much higher load. Just remember that. So it's the same rod as well. So K, that ratio between K and L, I'm going to refer to that as the stiffness, or that angle steepness is in proportion to the stiffness of that load being applied. Right. What have we got here? Yeah. Now we're starting to talk about time, over time. I kind of wish I'd put this slide a bit later on, but it does refer to something. If I hang a rod on a roof of something and I put a heavy weight on it and I leave that load on over a long period of time, what's going to happen, even though the load itself has its initial elongation of the rod, but after that, what's going to happen over a long period of time? What would happen?
You just stay like that if you take the weight off.
No. I've now made a short sign, yeah? I've got a brass ball or something heavy, yeah? And I've got a rod. What's going to happen to that rod if I just leave it like that for, say, 25 years? Well, you think that'll have fatigue? Fatigue or load? Yeah, of course it will. And this is what this is starting to talk about now. So S is now a measure of time, where before, when we were talking about on the previous slide, here we were talking about the magnitude of the force. Now we're not. We're keeping the force the same, but all we're now going to do is elongate it. Now it's got it in seconds, but it could be seconds, minutes, hours, days, weeks, years. Over a period of time, we'll have fatigue on that material as well. There'll be a displacement. So that's something that would be thought about for various structures, depending upon what it is we're trying to design. And we do indeed use that. We call that creep. And some materials we don't even bother about it, but other materials we actually do have to consider this factor. We call that creep. Or for concrete, we talk about fatigue. Metal as well. Right. Now we're going to get into the heart of Hooke's law. Hooke's law starts talking about this linear elastic and then non-linear plastic behavior. This photo was put in, I think they were trying to talk about timber. For timber, we do talk about a period of time. Okay? So, say that period of time is a number of years. It's not a number of seconds now, it's a number of years. And that slip or that creep has happened. What you'll find is if you then take the load off, it's never going to come back to its original shape. It won't do that. However, what will happen, it will come back to a point. It will still be deformation from the original. And that will be elastic displacement. For this part, for the load going back on again, and with the permanent displacement. That's the sort of thing we're kind of getting ahead of ourselves now a little bit. But again, on this sort of bridge here, we would definitely find that sort of scenario happening. You all remember in first year when we built those cardboard Dyson modules? Remember those Dyson module things? I had to account for that in this. Actually, there's a slide you've seen before. We had predicted total displacement. I worked all this out with a bet of about 7 engineers. I worked out all the maths. They waited until I put my first bet in and they all went underneath me. I came last. We actually worked out who would be nearest it. So I worked it all out. I divided my answer by 2 and everybody then went underneath what I predicted. I lost a bar of chocolate. I was quite annoyed. Right. Okay, I've left this in. Well, that's quite good. I was asked to take this out because you've been taught about this elsewhere. Has Juan been teaching you about viscosity in tarmac? No, okay then, we'll talk about it now for 2 minutes. There's a lovely experiment where they took some bitumen and they put it in a glass and they've left it for, we'll find out in a second, we'll find out in the next slide, from 1927, the experiment started. And they literally, bitumen is a liquid and it moves, but it moves incredibly slowly. There was a slide in here where I took this module over, which I had to remove, of big glass frontage. People up until quite recently used to believe that glass behaved also like bitumen. It was actually moving. I'll show my point first of all. There's the experiment here. I believe it's still running to this day, where the bitumen sitting in the funnel like that from 1927, and there's a number of drops fallen, and I think it took 10 years for the first drop to fall into the glass, and yeah, so it's still going. They used to claim that glass was the same, and nobody ever questioned it. And you were probably even taught this yourself at school, that glass is flowing. I was taught it at school. Absolute nonsense. Someone done some scientific research on it, i.e. they went round all the old buildings where the glass was thicker at one edge rather than the other, where they were like 200 years old type buildings. And what they found was, it's nonsense. When they used to make glass back in the day, they would blow a bubble of glass. They would then cut that off, fold it out, and make panels out of it. And in the old pubs, at the bottom pane was that bit at the bottom of the bubble. It was a bit weird. They use that as a decorative panel and small panel for old pubs. Am I showing my age now, yeah? There are some old buildings that have small panels in and every so often there's a panel with a little nodule in the middle. That would be from the blown glass, and it would be the bottom part of the bubble. But the rest of the panes, it would be predominantly where, however, it was put in. So to find thicker glass at the top or the side, it wasn't all at the bottom. People actually thought that glass was behaving like water. It wasn't. Anyway, we'll move on. I'll get back into like steel or other materials just now. So again, for yourself, this is more of a recap of what you've done with Juan. We've done all this with Juan so far, yeah? This sort of thing. Good, right. Right, now let's have a look at this linear elastic relationship, i.e. Hooke's law. Because that graph is the same graph we had before, even though I do think that's a bit exaggerated. In the real graph, it is a little bit more linear. You will see a bit more linear behaviour. But for simplicity, we're showing it like this. Because Hooke's assumption, it's not a law, it's actually an assumption, is actually a fairly good assumption. And engineers, we all use it to this day. So the equation you had before, force equals K divided by L, which is essentially stiffness, that angle, right, times delta, the elongation. What we find is K is a constant value. I haven't even told you what K is yet. All I've told you that K divided by L is stiffness. That's all I've told you so far. So, but we know that K from this will be a constant value. But what value? Right. Stress and strain. You've been taught this before at high school, I believe. Right. Stress and strain. What is stress? Stress is a force over an area. So if I have that surface area over that table, the stress underneath that big is force over area. Strain. What's strain? Sorry? Kind of, yeah. It's this is a good thing then, right? So for stress, force over an area, if we write this down in units, okay? So the axial, tensile, or compressive, yeah, that's fine. Right, I've been stupid. Right. Tensile or compressive can be newtons, force, divided by an area, a kilomillimeter squared. So that unit is important to know. You want to know what units things are in. The strain is essentially millimeters divided by millimeters. Let's have a look. We've got the elongation, that distance there, divided by the original L. So it's just millimeters divided by millimeters. Don't be naive and think, oh, that's just unitless and I'll not remember to think about the unit. In this module, I'm going to help you to write down what those units happen to be if it is a ratio. If it's a ratio that you know what the units are. There will be some ratios that we use that you don't know what the units are, and that's fine. But when you do know what the units are, do yourself a favour, jot them down on the paper. Right. So the stress strain curve has a relationship. And here, so there's your next equation there. E, or the modulus of elasticity, equals stress over strain. And that's quite an important equation to remember. We've got the force displacement relationship, seen that before. Now it can be rewritten in terms of stress and strain. Force equals stress over area. and then delta, or the elongation or shortening, can be rewritten as strain multiplied by the original length. Okay, does that make sense? If it doesn't make sense, go home tonight, take some paper and sit and just work through it until the penny drops. There will be quite a lot, not too much, there will be quite a lot of equation manipulations. And the best thing to do, honestly, cheap white paper, steal some from the photocopier if you need to, and just sit and just go through it. Right. Let's rearrange to give us this here. And now we've got K. So just rearrange that. We can get stress. So we've got stress over strain multiplied by A equals EA, modulus of elasticity multiplied by the area, which equals K. So K equals that or that. Perfect. We now have a better understanding of what K is. We also know that K is constant as well. Now, I will put some caveats on that. These are assumptions that we're making on a material of live test data. There's boundary conditions for all of this. Oh, sorry, you write it down? Sorry, I'll keep it up till you write it down. I think what I'll do, I'll actually just put the recording online for everybody. There's maybe a bit much in this. Right, we're all good to go? Right. Okay then, the axial stiffness. Remember this was this, what used to be K up there. Same equation, just we've got EA up there now. Of the rod as a function of material. So this is a function of the material properties, the elastic modulus and the geometry, the cross-sectional area. Final remark. Yeah, so I've already said this multiple times, it's just an approximation. However, we use it to this day, all engineers use these assumptions. Right, exercise 1. So with what you've already got, what I'm going to do, make some space for myself. What to do is, this is the exercise. Can we calculate the elongation of the rod, delta, with these parameters? You already have the equations that you need. So we've got force as 400 kilonewtons. We've got the rod as 800 millimeters. There's a wee clue there. Has a circular cross section on a diameter of 35 mil. And it has a modulus of elasticity. We tend to write the MOE down in different ways. I keep calling it MOE. It's written as E, and there's other names for it as well, but it's just modulus of elasticity. We have all the data that we need. We should be able to calculate that. Give it a wee shot, and I'll get myself set up. Let me just change the application for a second. I do apologise. Oh, this is the same exercise with my notes there as well. Cool. Right. What time is it? Oh, we've got loads of time. We've got absolutely loads of time. Let's slow down. Right. Right. I'll get with you then. I'll see how he's rolled in first. I'm going to give easy advice in a few seconds. I'll leave the calculators alone, or don't touch the calculator to the very end. No, I'll give you a word. I'll be okay. I'll do it. That's right. Yeah. Oh, well, then yeah. Cool. I'll give people a chance to actually finish what they're doing. It's quite good to. Is Adam Smith here today? Which one's the look? The look. Yeah. My word, you've changed since your photo was taken. And you're Liam, yeah? You're not. No. Okay. How are people doing? Anyone think they've got an answer or think they've worked it out? You have. Who's in your pistol, your final answer? So, you have one wrong, you've got the correct numbers, but this is actually a perfect example of what I want to talk about. There's more than one way to solve this, by the way. Let's try what way you've done it. No, that's what you've done. So you've done it how I'm going to show you how to do it. Right. So see in this example here, what you want to do, you probably feel the stress or even in real life. 1.5 this is what places that way, right? It's absolutely tiny number. I'm actually say it's a positive, right? You look at it and go, engineering judgment, this appears and we have on the mathematical error. And in the exam, if you think the numbering for option, please write that in. But then knows that we then know that you're then doubting what you've got. And then there's real life what you're doubting, and you then work out again, you go through it again, except those times and double check. Right? And that's we all do this, we all double check what we do. Right, or we just stop and help just to make sure the data we put in. So you've got that was about that. So you've got a notebook somewhere, which is kind of what I wanted to.
Doesn't get really all these
This is what you should be I should calculate it and double check. Right, anything else that you've got? Right. How you done this?
I don't know all the way up on my big examples.
You have done we have been shown that. Me, about me. Oh, no, it's what can you call again? What's that one? What is can you call?
Yes. Yes.
I think everyone's done it the way how I'm going to first show you. So what we're going to do is we're going to do it the way how a few people have already finished it and completed it. Did you get the correct answer? You did, perfect. And then what I'm going to say is do it again, but do it a different way, and I'll give you a wee hint. Right, and I'm going to do something a bit weird. It's not normal for people to do math the way how I'm going to do it just now. It's a bit different. Just go with me though, because it might help you going forward. So what is it that we want? We want that delta, the elongation. So I'm going to write this is my backwards way of thinking. Remember, heavily dyslexic. There's delta. I look at my cheat sheet. There's my cheat sheet here for today. There's all my equations that I know that I've got. I look at those and I think to myself, well, what equation has got delta in there? So there's delta here. So there's the equation there. So if I just go, so there's a valid point. I'm going to rewrite that equation to suit me. Remember, this is what I do. I'm dyslexic. It works for me. It might not work for you. Maybe you don't need this. I tend to do it all the time. What is the equation in 2.3? Yeah. So we've got the equation we've got is strain equals L. I'm going to rewrite that, and I'm going to go. Anyone seen anyone do this sort of thing before? Yeah. So I'm going to use that. I want this one. I've got these two here. Make sense? Right. Now, I have L. Now, actually, what I would normally do is, I would actually write out, I saw some of you doing it as well. Some of you are writing out all the variables that you actually know. So we know force, we know length, and this is where one person might have tripped up originally, was the units. So when writing it out, I'm going to go back to the start. I can take my time. I've got lots of time on this. So force equals, pardon me, force equals 400 kilonewtons. Length equals, at this point, I'm as well putting everything in the correct units at this point, rather than waiting to the end. Because for you it was really easy, because you knew what the problem was, and you could probably have fixed that without even recalculating it. However, when the equations get a bit more interesting, you definitely won't. It'll be more of a mind mess up. So get in the habit of doing this. Write all the variables out again. L is 800 mil. What else have we got? Diameter equals 35 mil, and E modulus of elasticity, sorry. Right, now we've got everything there, and I've converted the length to millimeters. Now I can actually start playing with it. Come on, move. Let me just make this a bit smaller so we can save some space. Okay. And what I had before, I had all of this before. I was going to do that. So I'm just going to go, what do we want? We want delta equals strain times L. I have L, but I don't have strain. So I'll put strain down. Strain is what I want. Let's find the equation that's got strain in there. Probably 2.4. So I'll do the same thing. I'll do a silly triangle. This helps me, doesn't need to help you enough, but it helps you, use it. So what I've got, that's what I've got. Right, so I want that, so it's just going to be, there's my equation. I've got E, but I don't have stress, so I'll put stress down here. Stress, we know, is just, sorry, I can do the triangle, you don't need to do the triangle for this one. Force over area. We know the force, we should be able to calculate the area. The area is just what? Pi r squared. So from that you can calculate the area. The area ends up being, I think it's 9612625. Right? And now I can start going the way back up, and I get to the correct answer. So you see, so far I'm not using a calculator until I know I've got everything sorted. Right, why don't you do that now and work out the correct answer on your own paper. Once we've got that, I'll show you a second way to do the exact same thing. Charlotte and I will remember names. You Eden. Yeah. I'll get there. Go on. There's another way to solve this. Find it. You got it as well, yeah? You're thinking, right? Yeah. Awesome. There's another way to solve this. Oh, right, let's show him. Do it that way first. Do it that way as well, then, right? You got it, right? What way did you do the same thing, yeah? Yeah. Do it that way, but just for a bit of repetition. Repetition makes you learn. Yeah. Right. You learn what's waste there, yeah? You can tell one of them. It's what don't see that. That's what it don't see. Oh no, the answer's correct. Sorry, what is your answer?
0.063 mil.
No.
Okay.
Right, I'll give you the answer. I'll give you the actual answer, right? However, on the slides after this, it's all broken out. I'm not going to not give you how to do it. Just in class and that. But it's all there for you. Right, so that's the final answer that you're going to get to. That's what Aidan and Charlotte got, and a few others as well. Finally, I will remember names. Archie. Yeah. Aye. However, Finlay and Archie done it a different way. How about I show you how they done it, and you're going to kick yourself. Because what they done is a hell of a lot less work. Did you get it, Charlotte? The second way?
No, I've only tried the second one.
Right. Well, just go for a laugh and just do it anyway, yeah? It is a different colour pen. They just looked at the bottom here and went, oh, that's handy. Just look at that bottom one. So they just wrote it out. They wrote force equals, sorry, you can't see that. Why can't you see that? What's happened? There we are. Right. Force equals E-A-L delta. Without any hassle at all, we just rearranged it and just got delta equals F-L-E-A. Right. Obviously, we can calculate A, and you've got everything else. You've got force, you've got length, and you've got E. You've now got A. Then you get the answer there, and it gives you the exact same answer. Make sense? Much faster than how we done it the first time. Much faster. Right. These are obviously switched on. Most folk don't see that straight away when I do this. However, what I'm going to say is in this module and in real life, to be honest, real life problem solving, this is what engineers are. That's what we are. There's always another way to look at it and think, can I calculate it a different way? Are there equations or is there another toolkit? Can I use calculus? Can I use complex numbers? There's another way to calculate what I want. If I calculate it two ways, for example, this is a stupid example. We were in a pub quiz years ago in Germany, and they're all scientists. I'm an engineer, but they're all actual physicists, scientists, and chemical engineers. And in the pub quiz, we were asked, "What's the volume of a sphere?" And nobody could remember, which is quite stupid. Imagine not remembering that. However, we all sat and worked it out, but I think we worked it out in 3 different ways. All got the same answer. Yeah, that's what I was going to say something there. Yeah, and so in real life, there's always more than one way to work things out. So that's quite good. Try and get your head around both ways, though. Yeah, go home tonight, play with it. You do have all of this on slides, so on the middle page. So what I'm doing here by hand is fine. You've got it all. Right, let's do the next one. And what I'll do is I'll move this down, just in case you've not got my note. What's different with this one?
The square.
Sorry?
The square.
It's a square, yeah. And what's the question? Calculate the final elongation of the rod. So it's not actually much different at all. No, it's pretty much the same. Kind of. Give it a wee shot. Whilst you're doing that, I'm going to talk some nonsense in the meantime. I quite like this module. Quite a good module. It's quite a lot of background theory that you're going to need for the rest of your engineering career. I wanted to change it. In the lab experiments that we're doing, now I've not had time to change it, so it'll be as it normally is. We'll be using lab downstairs with really expensive equipment. I want to do it with classroom equipment, classroom cheap, easy to do lab experiments, which I thought would be way more fun and a lot more hands-on. However, if I get a chance to actually do that, I think we'll actually do it anyway. For the 2 direct entries, were you here in trimester 1? You were. Right. So if everyone's done the McCulley method, I could swap out that lab for us doing a classroom lab instead, if I could get my apparatus. Cheers, catch you next week.
Could we access the recordings by the end of today, or it will be?
Probably tomorrow now. Probably Wednesday, to be honest.
Okay, better.
That's alright.
Bye.
I'm messing but only if you're Sean, of course. Done. I went onto the student portal and downloaded photos for a class.
I've not got a number for
Anyone got an answer for me? No? What you got? Shut up. You got an answer? Was it? Yeah. How many ways can you do it? It's quite easy, isn't it? Because we've got a bit of time left, because today's class was more of a light-hearted attempt of getting you into it. What we'll do is we'll show you. Oh, 1 second. I'll show you some. There's a pen there. Sorry. I'll show you the tutorials. No, sorry. I'll show you the last year's entries for the coursework. How to do it. I think on that bottom row, I've got the correct answer. Yeah. 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 And you've got it. Got it. Yeah. Cool. Something is as this thing here. Right. Cool. Oh, so all of that, are you? Do apologise. I'll just make it smaller. Right. Okay. Nice and straightforward. Right. What we'll do? Y'all got that? Easy. My suggestion with this module is to do the small, simple exercises each week. Don't put them off. Just do them each week, and by the end of it, it'll be a fairly stress-free module. If you don't do that and you leave things to the latter end, it then might get a bit much. I want to let me give you some positives about this module. We've got an industry sponsor sponsoring this module. So the person with the highest mark gets a prize, and they get bragging rights on their CV. And the sponsor is, who is it again? There's a few. This one is structural timber. Let me tell you now. Structural Timber Trade Association, that's it. So they're the ones sponsoring this module. You'll get a wee prize. They also sponsor 3 other things as well. They'll sponsor the best dissertation in timber for master's level. They also do the undergraduate level, the best one in timber. They also sponsor another class to do with the architectural technologists. So that's not you guys, and they sponsor this one. So it's going to be the highest mark overall. That is your courseworks and your exam. Okay? And it's just the highest mark, winner takes all. Also, this class last year, we ended up hiring 2 of the students from the class to become interns, and they now work for the research centre that I'm a part of. So that's quite good. I can't say right now I've got 2 places for this summer. So we started off in the summertime. That's when we started their employment, and they worked full time over the summer, and then we ended up keeping both of them, and they still work for us just now. Well, I say as one for Void Tech and one for Ecosystems Technologies. So I know that we've got another 1 definite place to fill. It could be somebody in this room, or it could be somebody in another class, but there's potential. As I said last year, it was 2 people from this module that got the job, mainly because both those positions, one was to do lab testing, quite a lot of lab testing, and since then they've moved on to other really cool things. And the other one was to be a design engineer with heavy oversight. So they're designing, you know what SER is? An SER for building work. So people build these modular timber buildings, but they're building out of homegrown mass timber. So Napier has funded this to an excessive amount. So the commercial company that do the commercial wing of that test research work hire quite a number of our students and former students. So I know I've got another one of those to go to identify. So it could be good fun. Right, let's have a quick peek at what we had last year. As I say, I've got this person's permission. They were to talk to this individual, they'll be fine with it. So you've got 3 coursework to do. I'll show you all 3. I blank that for a second. I can. Excellent. I'm not even showing you this person's mark, but I'm not showing the whole class's marks. That'd be inappropriate. So this isn't me telling you what your courseworks are just now. We'll do that in another class. Just that we've got a bit of extra time here. I want to just show you how similar or how exactly the same all 3 are. Just the mathematics is slightly different, right? Take blank off. Come on. Oh, it's on, right? Perfect, right. Perfect, right. Let's get past the person's name. If I can't person's name's there. So, okay, that's fine. We all know who it is now. So they've got a nice front cover, the front logo at the top, make it look nice and plain. Table of content, small introduction. Please try and be at everything in this module. The more things you miss, the more difficult it will be for you. So be at things, take photographs, take lots of photographs when you're in the labs. I'm not asking for the world here. Just a fairly simple report. There's the first test that was done. Was it yourself that was saying that would be a shear failure? The draft that you get from this is quite interesting. There's the graph there for this one. It gets up to what's called an F max, then it stops, and then it'll never take a higher load. It won't take any more load than that. Once it's taken its maximum load, and it's not falling to bits, but it'll never take as big a load as it did before it broke. Yeah, the resistance isn't strong. So that's failed at this point here. We then take that linear. Now you'll get taught more about this in the coming weeks. You've only had an intro to this just now, but we then take this area here, actually about that area, to be honest, and blow it up. And this is this Hooke's law or Hooke's assumption we said. It's not perfect. You can see the data is not perfect to that dotted straight line. And we get what's called the goodness of fit, or R squared value. Just done all of that. Second test, third test. And this person obviously came to all of my tutorials, and I'll show you how to set everything up, show you how to make graphs, show you how to take things in and out, and also how to draw within that graph as well. So she's copied my format exactly, put in the equations. It's not difficult. And that there earned that person 100%. So you see what I'm saying? I'm not asking you to spend 5 nights on it. It's a 1-night job. Okay? Fairly straightforward. However, this test, I'm going to call it this one here, the first one we do, parallel with the grain, is the easiest one of the lot. Right. I'll not explain why just now. I'll show you the second one. Sorry, blank. Yeah, I got permission from that one person, but I haven't asked the whole class, so I can't show you. Now, obviously, your data will be different from this student. Oh. So it's quite obvious to see that I do believe in 100%. That is quite easy to get 100% in this module for the coursework part. Okay. Now, if you remember the last one that this student put in, now how we mark it, now you'll find most lecturers will use this sort of system. They'll tell you up front the categories of how things are marked. Okay. They'll tell you you got a percentage for presentation, readability, technical content, figures and tables, and conclusions. They'll give you categories and they'll give you the weighting for each category, and they'll mark it literally on a sliding scale. It's a quick way of doing things. So that's quite common. So you've got who have you got? This. What other modules have you got? Geotechnic.
We've got Vicky for soil mechanics.
Yeah.
And then some guy, I think it's Mark or something for maths.
Oh, mathematics, right. So you've got soil mechanics plus this plus maths, right. Fair enough. Right. This one here, the string is kept the format exactly the same. Same thing. Now, you'll notice though the samples are different shape, different size. So the question reports on that. This test and this one now. This is actually a lot harder mathematically to do. And this is where attendance at the Axial, so the E32 labs will be crucial for you. It's a bit more interesting. I'll show you why. But you can see the format of the report is exactly the same. And if you can understand the mathematics, which I promise you will, if you've done so well so far already getting the numbers correct on this, trust me, you'll understand the maths and how to do this. It's just how to do it in Microsoft Excel. I'll need to show you how to do it. You have to draw lots of things into the graphs as well. And there's lots of extraction from that graph you have to do. Why is my graph not failing? There's no F max there. Now again, I'm jumping right ahead. I wish I had got it now. I've got one in my lab. When we got a new machine, we spent £80,000 on a new machine downstairs about a year and a half ago. Personally, I'm quite jealous because in my lab, we've got a much older version of the same machine, and the newer one is much nicer software. Well, the chap who got it, Gary Britton, was playing with some of the samples that I gave him for this class, and he's not a timber person, he's a concrete specialist. And he thought, well, you just break things till they go bang. Because normally with concrete, they go bang, don't they? They make a mess, and they have shards of concrete flying everywhere. Well, he was expecting the same. But when you compress wood like this, that's not what happens. He just kept this machine on. And he started off with something that size. Now it's like that size. And it's amazing. So I kept it. I mean, I wasn't there when he was doing it. I mean, he could have started a fire, but he probably did start a fire. When you compress wood like this, it shears and it no longer takes a load. When you compress wood like this, it will continue to take a bit more load, a bit more load, a bit more load, and it'll keep doing it. But that angle, now before we talked about the angle of the stiffness, the K divided by L, and I talked about the angle. If that angle is steeper, it means the material is very, very stiff. Well, this material here starts off quite stiff, right? But then it gets weaker and weaker and weaker. And up here, now if we had left this test running, I have to ask him, does he have the test data for the one that he actually did do? I'd love to see it. I bet it goes on like this. And the angle of it will be tiny, absolutely silly. And it's already failed, right? I mean, the timber's changed size dramatically, absolutely dramatic. So, but it's already failed. And when you're doing testing like this, it's very difficult to identify where the F max is. And that's what I'm going to show you how to calculate it. There's a correct way of doing it, a procedural way of doing it. And we'll talk about that. But you see the report, pretty much the same format as the previous one. Really, and again, they put in the equations for things, 100%. So if you've done the first one, and you get a really good mark, or I tell you, look, go and do this a bit better, go and show this on the graph, if I tell you that, then your second one, you implement those changes, as long as you understand the mathematics, as long as you are able to get the graphs drawn, which are Easier said than done. Where's the graphs? Right. And it's not just a case of drawing them, you also how did you get to the F max? Like the actual how did you eventually calculate the final F max? And there's an iterative process. You have to do it about 4 or 5 times before you actually get it. Right? So again, 100%, you see the mark up there. Nice and easy. Not difficult. The third test is actually a 4-point bending test. You've done a 3-point bending test with a concrete. Is it 3 or 4? It must be 3.
I believe it was 3.
Yeah, it wouldn't be 4. It's too small a beam, it's only that size. Is that right?
Yeah, but
Yeah, it's that size. But for everything else, we want to do a 4-point bending test. However, when we do a bending test like that, 4-point bending test, again, it's back to that first graph. You just draw the graph. You find the F max by going equals max, open brackets, range, close brackets, and you find the F max. Stupidly easy. Right. However, the conclusions and write-up on it are also worth it. It's not a case of just doing spreadsheets and job done. Also the conclusions and you understanding what it is you've done and what you've found. What you've done. You actually see there, if you did happen to see that, the marks are quite good. The marks genuinely are quite good for that class. Right. We can finish early, I suppose, but what I would say, anything else for me to do? One more? No, it's not good. What I would say is, there is a class test. I've not decided yet how I want to run this test. I'll be in a larger room, so these are my cheat sheets that I'm not going to give you, right? But I think you're all intelligent enough to make your own cheat sheets out. What I want to know is though, and that's week 2, week 3, week 4, week 5, and for the class test, pretty much all you need. I'd rather not give these out to you for the class test. So I want to know if that would be a problem, being able to memorise equations. I've not decided yet, so you can talk to me about it in the next X number of weeks. We've got loads of time. You know what I mean, though, yeah? I don't know if I want to just say, right, in the exam you'll have this. I think you should want to know this yourself. The reason why I'm saying that, a class of mine, when they sat their exam in try 1, couldn't remember 2 simple equations. And it's just wrong. These guys should know. Like the ones that you need to know, I'll scroll them up for you, but I'll write them up here. The ones you just need to know for
is the test like in person, by the way?
yeah, of course it is.
Just checking.
Yeah, sorry, yeah. On the module descriptor online, it's in person. Sorry, okay. I thought you'd have known that. Sorry. Sorry for my tone of voice there. Right, so there's two scenarios you've got. So in a book like this, or I would just go and buy this book to be honest, but I'm going to give you I'm going to put it online for you as well. You've got things like deflection calculated. You're unlikely to remember how to do that, but the moment calculations, please remember your moment calculations. But they're the things you're going to just need. You don't need to remember all of them, there's way too many. And I'll be honest, when I'm doing a project, which I'm doing a few at the moment, I quite often I do double check my memory, if that makes sense. If I'm not the best at it. But if you're able to memorise certain things, these are things you're going to want to know. Because in other exams, they'll expect you to know this, like later on years, they'll expect you to know this stuff. So for a UDL, you had this before, haven't you? Yeah, what's the equation? So moment equals, we know it's divided by A, right? So what's on top of it? It's obviously load times the length. Yeah. So what messes people up sometimes is you've seen that written in slightly different ways. How it's written in my book here, which I think is absolutely bonkers, they use capital W to mean the total load, right? And they use small w to mean the UDL, or let me just rewrite it for you. UDL times L, or you could even rewrite that if you wanted. Okay? Or just remember that it's a total load times L divided by A. That's the moment for a UDL. Point load in the middle, bit easier. Or is it? Anyone remember that? No. Okay, what we'll do for next week. That's front page. But you know how to do the Macaulay method though, don't you? You've been taught it.
If I could tell you to do it, I don't remember it.
That's right. Yeah. They're the sort of things you'll just want to have the ability to be able to do, right? And believe it or not, I know it uses calculus, but it only uses like 2 rules in calculus. It uses like the entry level stuff. It's really not hard. So try and have that at the back of your mind. Right. Also, whilst we're here, what would the reaction to theirs be for that simply supported beam? That would be just half the load. The load divided by 2, wouldn't it? So reaction A, reaction B will just be W divided by 2. Yeah? Yeah. That is, yeah. Right. So the moment for this is actually again, well, it's divided by 4, not 8. So that's a one start. And P is the point load. And guess what? It's just simply L. If you can remember those two for that, that'll make your life a lot easier. This is what a master's class kind of had to get a wee bit of help just before the exam. And that's shocking. Don't be that person. Right. I'll find this book and I'll put it online, but don't go telling them yet. I'll double check if we're allowed to hand that out actually first before I get in trouble. Right, next week. Let's have a look at the calendar again, just very, very quickly. Because yeah, it's not until week 4 that we're going to have the Axial tutorials. So next week, I'll be for a normal class. But week 4, we'll have a tutorial from 11 o'clock to 1 o'clock. Now, it won't be as long as that. I promise you we'll finish it. I will promise you we'll get done probably in half an hour, an hour max. But you'll do it yourself in Microsoft Excel and the computer suite. So it will not take 2 hours. That I can promise you. Okay? These labs here, though, an hour and a half. Yeah, that doesn't make sense, does it? We can fix that. What we'll do is we'll try to get that done in half an hour, and we'll go straight to that, get that done. That'll be finished. That's not going to be as long as it implies either. That doesn't need to be as long as that. The reason why it did take that long before is because you had 3 tests, and the older machine, one like my one in Seven Hills, is quite a slow machine, and things just might not work, and it just takes ages. For the new machine they've got, so we can do it in much faster time. So it won't be as boring and long-winded, but it should be fine. When you do come to these labs, make sure you bring your phone that's got a camera. Obviously, all phones have cameras now, but you want to take lots of photographs. This one here, this is an additional experimental lab that I was doing before, and that was to reinforce the Macaulay method and also the buckling constant. I made a mistake. Anyway, I might want to change that out and do something completely different, and do something a bit more tabletop experiment different. We'll see. Or we've got other experiments we can do as well, which might be a bit more fun. But this might change from what I've currently got planned. Your class test. I think rather than starting at 9 o'clock, it will be a Monday. It will be week 14. You've got a week 15, but we'll do it in the week 14. So when you're talking to your other lecturers, they're going to ask you when are your class tests or exams. Yours will be in week 14. So we'll try and encourage them. And it's Vicky. I'll talk to Vicky, and I'll encourage her to do hers in week 15. Make sense?
Yeah.
Right. Otherwise, you've got 2 in 1 week, and that sucks. We don't want that. And also, come back and tell me next week if these dates here need to be moved up to a bit if need be.
Okay.
I don't want to bring them down this way. Cheers.